In this video, we're going to talk about velocity in two dimensions. Velocity can be defined as the rate at which position changes, and we use the equation v for velocity is equal to displacement over time. So it's that changing displacement over time. So velocity is a vector. That's the other thing to remember. And vectors have both a magnitude and a direction. So if you were driving down a highway, it wouldn't be enough to just say that your velocity was 100 kilometers per hour. You would actually have to say your velocity was 100 kilometers per hour north. We're going to put a direction there as well. To indicate this direction, we will generally use the XY coordinate system. So we just draw on our XY axes here, and we base the direction off of an angle from that x-axis. So whatever the vector is, we're just going to use that angle there, and that'll indicate the direction. So we always need a reference point, and usually the reference point will actually be the x-axis unless otherwise stated. Okay, let's try solving a problem here. You are standing on the western bank of a river watching a swimmer swim to the east at 1.20 meters per second. As the swimmer crosses the river, he is also being pushed by a current that is traveling at 0.35 meters per second north. What is the swimmer's velocity with respect to your position on the western bank? It's really important to indicate or note the reference point here in this problem. And when I see right at the end here that we're looking with respect to your position on the western bank, we have something that's stationary. And that's really important. So what I want to do is draw a little sketch. And it's always very important to draw a sketch so you can kind of get an idea of what's going on when we're dealing with multiple vectors like this. Now you don't need to have an actual picture of a river, but I think this will help us just to see what's going on here. So I'm going to first of all just kind of indicate a scale here. And so I'm going to make this direction east, and then I'll make this direction here north. All right, so I'm just putting in that scale so I can keep track of my vectors here. Okay, so let's bring in our first vector. So here is the direction east across this bank that the swimmer here is swimming. And we know the magnitude of this vector as well. It's 1.20 meters per second. And we know that that's going to be to the east. And then I'll bring in my current. Here's my river current here. So this is traveling to the north. And I'll even write the magnitude in for this one. This is 0.350 meters per second. And the resultant vector is going to be connecting the tail here of the first vector to the head of the final vector. And so I can bring in my resultant here. This is actually what I'm going to solve for. So this is going to be the final velocity here. So with any motion in two-dimensional problem, I'm always going to be solving for two things. I always need to find the magnitude, and then I also need the direction. So the magnitude we can find using the Pythagorean Theorem. And we have a right-angled triangle here, and I can solve for the hypotenuse here. So let's go ahead and do that. So here's the Pythagorean Theorem. I can see C is going to be my unknown side, and then A and B are the two vectors that I already know. So I can rearrange this, take the square root of both sides here to get rid of the squared on that side. And I'll end up with my equation to solve for C, and then I've plugged in the two vectors that I know there. Those are the both of those sides there, and I do need to square those. And I can plug that into my calculator, and I will get a magnitude for C of 1.56 meters per second. So that was his velocity. That's the magnitude part of it. So that's how big this red vector is right here. The other thing I have to do now is I need to solve for this angle right here. So I need to find that angle. And to do that, I can use sine, cosine, or tangent. Remember SOHCAHTOA. That's that handy acronym there to remember what these things mean. So we could take the sine of the angle is equal to the opposite over the hypotenuse, and then the cosine, and then we have tangent. And what I'm going to use here is I'll go with sine. So I'm going to take this first one here. I'm going to expand this to see what it's actually like. You can do this with any of them, but the sine of theta is representing our angle, is going to be equal to the opposite side, and I'll go show you where that is on the diagram here in a minute, over the hypotenuse. That's what I just solved for. So let me go back here and show you where those things are. So here's my angle, and I'm looking at the side opposite of that angle. It's straight across. So this side right here would be the opposite, and then in red here we have the hypotenuse. And so this is the angle I'm going to solve for. I'm going to have to rearrange this a little bit. I want to move that sine over to the other side. So what I can do is I take the inverse sine of both sides, and then the inverse side of this side, and that's going to cancel sine on this side and leave me with just theta. And here's what this equation looks like solving for theta. So I can solve for that angle. So I can just plug in my numbers here, and then I can punch that into my calculator, and I will end up with an angle of 12 degrees. And so that's the second part of my answer here. So I have my magnitude and my direction. And so that would actually be my final answer. I could say that the swimmer was traveling at 1.56 meters per second at an angle of 12 degrees. Okay, let's add a little bit more difficulty here. So here's kind of to expand on this problem a little bit. If it took the swimmer 8.5 minutes to cross the river, how wide is the river? So we're bringing in a couple things from our understanding of velocity. So I'm going to bring my vectors back in here. And this time I'm going to kind of address things a little bit differently here, because I know already the angle. All right, I found that in the previous problem. So I know that this is going to be 12 degrees, and I also know this hypotenuse here to be 1.56 meters per second. So what I want to find here is I want to find this green vector actually right here. I want to know exactly how wide this is. So I don't want to know this vector anymore, because the swimmer actually swam more distance than the river is wide, because the current was also pushing him along to the north. So he actually swam a little bit extra. So this is what I want to actually know here. I want to know what that is. And so what I can do is I can use the equation here for velocity. Velocity equals distance over time. And I can actually solve for that distance. Actually, displacement. That's displacement over time. So let's change this around. I'll multiply both sides by time to end up with distance equals velocity times time. And I know my velocity. It's right here, 1.56 meters per second. And I know my time there, 8.5 minutes. I do need to change that into SI units of seconds. So let's do that first. So I have my 8.5 minutes and multiply that by 60 to get my time in seconds of 510 seconds. Now let's go ahead and plug in our information here. So I have 1.56 meters per second times 510 seconds. And so the displacement of our swimmer here is going to be equal to 796 meters. Now that's the total displacement that he swam. That's not going to be the actual length of the river, because I still want to solve for this vector right here. So to solve for that side, I'm going to use cosine, because the cosine of theta is going to be equal to the adjacent side of the triangle over the hypotenuse. And when I'm looking at this angle here as my reference point, the adjacent side would be the one beside it. So that's actually what I'm going to solve for. So I can rearrange this by multiplying both sides by the hypotenuse, and I'll end up with the hypotenuse. Actually, I'm going to move that over here. All right, so the hypotenuse times the cosine of theta is going to be equal to the adjacent angle there. I'll put that in parentheses. And so we know the hypotenuse is 796 meters. Okay, I'm using the distance now because that's what I want to solve for. And I also know the angle is 12 degrees. And so when I plug that into my calculator, I'll find that the adjacent side is 779 meters. And so that would be the answer to the problem. The river is 779 meters wide. And that is velocity in 2 dimensions.